Okay, so here's my favorite wave simulator. And here's me. Hi. Okay. I like this program Snagit when I'm showing my screen. It's better than my whiteboard. Okay, so the wave simulator. So now I want to, first of all, before I talk about superposition of waves, I want to show you just the equation of a single wave, right? Here's a single frequency wave. It's got, and this is a position graph, right? In time, we can start it going and show what happens in time. But on the screen, you've got amplitude or y or psi on the horizontal and position in space on the right. So this is what a wave looks like in time. Okay, so I'm going to go ahead and stop that and look at the wave function up here. Now it's probably small in your video, and I don't know if you can even see it. Right now, the amplitude is 0.5, k is 3, and omega is 1. So the wavelength is 2 pi over 3, and the period is 2 pi over 1, or something like that. Oh, I guess that would be 2 pi. So there is no phase. Now, because I had already started it, I wonder if there's a way of resetting it. There, okay. No. All right, I'm just going to put in a new wave function and see what happens. Okay, I'm just going to change it to an omega of 2. Boom. Huh. Wait. Okay, I'm going to pause the recording. Okay, I see what I was doing wrong. The origin, I was thinking was the left axis, but the origin is right in the center here. This is the origin, right here. So notice that this sine function starts at x equals 0 because there is currently no phase. And I just want to show what I've been trying to say about how the phase sometimes just doesn't matter. If we're talking about a wave that doesn't move through space, then the phase does determine the initial conditions. But if we're talking about a wave that moves, the phase doesn't matter because the wave starts moving and the phase just determined where it started. So notice that if the phase is 0, then the origin of the wave is at 0, right? That the amplitude is 0 at that point. I'm going to go ahead and add a phase into this wave. So I'm just going to add an arbitrary number. I'm just going to add 1. Okay, so now the phase is 1. I'm going to hit return. And notice what happened is the wave shifted. Right, so at x equals 0, now it's something, right? The amplitude of the wave at that point, and I said I'm going to try not to use the word amplitude because amplitude we're going to reserve for maximum displacement from equilibrium, but the size of the wave at that point is something between 0 and a, because the phase is just some arbitrary phase. I can change the phase to something else. I'm going to change the phase to 1.5, and that's 1.5 radians. I think this is probably in radians. Oh yeah, and 1.5 radians is about half a pi. So it just changes the sine function to a cosine function. So now at x equals 0, it is at approximately its maximum. And if I had been made it exactly half a pi, because 1.5, wait a second, hold on. Sorry, I had to stop and think about that for a second. 1.5 radians is about 90 degrees. It's about half a pi. I could have made it exact and put that peak right at 0. But notice, so the phase, we can change the phase, which changes where the wave starts. But once I run it in time, then it changes, right? At x equals 0, the amplitude of the wave changes. I'm trying to trace x equals 0 as time goes on. So the initial phase really didn't matter if all we care about is the wave motion. Okay, so that's the first thing, is that we're just not going to worry about phases here when we're looking at wave superposition. We're just not going to worry about the phase, not at least at this point. Okay, so here I have a wave. I just changed the omega and k to each be 8, whatever that means. I just changed the numbers so that there's more peaks on a page. And so you can see that wave there. And then now I'm going to add it to a second wave. So that's the blue wave, is this function up here. I'm going to add it to a second wave. And the second wave, I'm making omega and k just a little bit different, but I'm making them the same again. And there's a reason why. In a second, you'll see. 7. So the red wave, I'm going to turn off the blue wave. There's the red wave. Turn back on the blue wave. There's the blue wave. Put the red wave on top. Okay, they're actually similar waves, but they're slightly different. And we can turn off one of them and propagate through time just to show you. Okay, so they propagate through time. Okay, so what I do want you to notice is that since for the blue wave, omega and k are 8, and for the red wave, omega and k are 7, that they both have the same wave velocity. So I've chosen a particular case where they both have the same wave velocity, because wave velocity is omega over k. So you can see they move together. But now let's see what happens when we add them together. When we add them together, oh, look, there you go. When you add them together, you get this wave blob. This wave blob, right, that has an oscillating term. This is the oscillating term, the high frequency term, the short period term, and then, or the short wavelength term, short wavelength term. And then you've got the envelope term, which you can picture an envelope, a sine wave or cosine wave, doesn't matter, around this wave. So there's the oscillating term and the envelope term, and then the fact that I've chosen these two waves so they move each at the same speed actually means that the oscillating term moves at the same speed as the envelope. So you can't see the envelope, right? But just imagine there's a wave here, a wave function there, and that envelope, a peak of the envelope is moving at the same speed as the peak of the oscillating term. Now let me go ahead and change the red wave. You can't see the blue and the red just because when you put them all together, it's sometimes a little hard to see what's going on. I mean, we can do that. It's a little hard to see what's going on. I'm just going to keep the blue and the red off and just look at the sum. This is the sum. I'm going to change the red wave just by a little bit. So I'm going to make it 6 for omega instead of 7, just so that it has a different speed than the blue wave. Now notice that the oscillating term, envelope term, when we freeze it in time, look pretty much similar to what they did before. But now what happens when I play it? When I play it, notice that now the envelope term is traveling at a different speed than the oscillating term. And so it's a little bit more complicated, that if you look at any of these peaks of the oscillating term, just follow a peak along, it's got a slightly different speed than the speed of the envelope term. I'm having trouble keeping up. Speed of the envelope term, just follow a peak of the envelope along. And that is because that comes out of that sum wave equation that we've written down in class. Now, it's fun to come in here and just try different combinations of omega and k and see what different kinds of things we can get. We're going to do that later on. But for now, I want you to just consider this idea that what we've created here is what's called a wave packet. This lump of waves, this little oscillating term inside an envelope term, which is just 1/2 of a wavelength, right? That's just 1/2 of the full envelope, which in our sum was just the cosine term, right? The cosine of delta k over 2 times x minus delta omega over 2 times x. That is that envelope term. And 1/2 of that envelope term is this little lump of waves, which we call a wave packet. This is what's called a wave packet. And so we can see as we progress that the wave packets move. The wave packets have these all kinds of interesting properties, but the wave packets move. And what we will find, or what we will state at least, we can actually model it here by adding in more sine functions, is that the more sine functions we add in, this is just a sum of 2 sine functions. This is actually a sum of a sine function and a cosine function, but it doesn't matter because, again, phase can change a cosine to a sine. This is the sum of 2 sine functions. If we add in a 3rd sine function and a 4th sine function, which we can just do, we could add that in to these equations on the top. I'm not going to do it right this second. What we find is that we can isolate one of these wave packets. We can make this part, which goes to 0, extend out further, and we can isolate a wave packet. This is what's really important in quantum mechanics. And so we can spread out these packets of waves. We can spread them out by adding in more sine terms, more sine terms, more sine terms of the right omegas and k's and amplitudes. And we can, thus if we can, we're isolating one of these little lumps of waves by making this 0 part actually just extend a little farther. And so we can add in another sine term and make this 0 part extend a little farther. Add in another sine term, make this 0 part extend a little farther. Isolate this wave packet more and more. So is there a way to have a single wave packet and no more. Not, not to never be able to see this one and only this one. And hopefully you can answer that as yes, if we that must be possible by what I'm saying, if we can add in an infinite number of sine waves. We can make this infinitely long, this zero part infinitely long, and have a single wave packet. And that is how we represent particles. Particles are an infinite sum of single frequency sine waves. And nothing wrong with infinite sums. We do it all the time. Fourier analysis, if you've heard of that before, that's about infinite sums of sine waves. We can have an infinite sum of sine waves in order to isolate a wave packet and represent a particle. That is what we do in quantum mechanics.